Hello everyone, I'm J Wildberger, and today we're going to be talking about the fundamental algorithm underlying row reduction or Gaussian elimination. This is a step-by-step procedure that allows us to solve a system of linear equations once that system is in matrix form, typically working with the augmented matrix of a system. Okay, so it's a step-by-step procedure, and it's reasonably straightforward, but there are a few steps involved. And to make it easier to understand those steps, we need to get some definitions clear in our minds. So let's start with leading rows, entries, and columns of a matrix. What do those words mean? So first definition, a row of a matrix is a leading row precisely when it is not all zeros. So it's got at least one non-zero entry in it. Second definition, a leading entry in a leading row is the leftmost non-zero entry in that row. As you read from left to right, you might have a few zero entries, and then you get to something non-zero. That first one that you get to is the leading entry in that leading row. And finally, a leading column is just a column containing a leading entry. So, for example, have a look at this matrix here. You see an augmented matrix for some system, and one of the rows is 0. This is a non-leading row. The other three are leading rows. So this row, and this row, these are the leading rows because they're not all zeros. The first or leftmost entries in those rows are the leading entries, and they're the ones that are circled. The 2 in the first row, the 4 in the second row, and the 4 in the fourth row. The leading columns then are the columns containing these leading entries. So these columns here, the first column, the third column, the fourth column, they are the leading columns of this matrix. Okay, great. Now, row-echelon form of a matrix. Okay, a matrix is in row-echelon form precisely when the following two conditions are satisfied. First of all the leading rows are above all the non-leading rows. In other words, all the rows of zeros are at the bottom. And secondly, that the leading entries, are staggered to the right as we move down the rows. So let's illustrate that. Here is a matrix in row-echelon form. It's in row-echelon form because you can see that the row of zeros is at the bottom. That's the non-leading row. The three leading rows are the first three rows. The leading entries are the circled 3, the circled 2, and the circled 8. And they are indeed staggered down to the right. As we go from the first row to the second row, we have to move to the right from the 3 to the 2. As we move from the second row to the third row, we're moving to the right from the 2 to the 8. Okay? So both conditions are satisfied. That is a matrix in row-echelon form. How about two examples which are not in row-echelon form? Well, this one here, that's not in row-echelon form. Why? Well, because there's a non-leading row which is not at the bottom. That middle row is a row of zeros. It should be at the bottom in order for it to be row-echelon form. The leading entries, they are indeed staggered, so that part is okay. It's just that the non-leading row is not at the bottom. And in the second example here, well, now the non-leading row is at the bottom, so that's good. But the leading entries, which are the leftmost non-zero entries in the two top rows, they are not staggered. As we go from the first row to the second row, we are not moving to the right. We're just going straight down. We have to move straight down and to the right. It has to be staggered move right, move right, move right as we proceed down the rows. Okay, so now we know what a row echelon form is. There's a kind of refinement of that called a reduced row echelon form. So we say that a matrix is in reduced row echelon form if it is, first of all, in row echelon form. And so in addition to being in row echelon form, we have two other conditions. First of all, that every leading entry is exactly 1. Okay, it's exactly 1. And secondly, that every other entry in a leading column is 0. Every other entry in the leading column is 0. So if we have a column which contains one of these leading entries, it's 1. From being in row echelon form, we know, in fact, that everything below that leading entry is 0. Now we're adding the additional requirement that everything above that entry is also 0. So the entire column consists of zeros except for the single leading entry of 1. All right, so consider this matrix here. First of all, the row of 0 is just at the bottom. So the non-leading row is at the bottom. That's okay. And what about the leading entries of the rows? They are these 3. Notice that this last column is, in this case, also a leading column. Okay. So here the leading columns are this one, and this one. These are the leading columns for this matrix. So we have these leading columns, and we have the leading entries now are 1. So that's one of the conditions. And furthermore, the entire column of the leading columns are all zeros, not just below the leading entries, but also above them. So if we look at this leading entry right here, then above it, there's also a 0. We know that below there must be 0 because the next leading entry is staggered to the right. Okay. So similarly with this one here, we know everything below it has to be 0 because the next leading entry is staggered to the right if there is one. But what is in addition now is that the things above the leading entries are also 0. So this thing is in reduced row echelon form. Okay, so now we're ready to present Gaussian elimination, which is the first half of this row reduction algorithm that takes a general augmented matrix for a system of linear equations and transforms it to a row echelon matrix. This is sort of the halfway point to the full algorithm. So how do we get a row echelon matrix from a general augmented matrix? So step 1 is that we're looking for a pivot entry. Okay, what is a pivot entry? It's the top non-zero entry in the first non-zero column. So we're going to be looking at columns. We go to the first leftmost non-zero column. So in the example that you see here, this first column here is a column of zeros. So we're going to ignore that. The second column, also a column of zeros. We're going to ignore that. This third column does not have all zeros. So it's a non-zero column. And we're going to choose the top non-zero entry, this number 3, that entry right there. I'm going to call that pivot entry. Okay, that's going to be the important point. And what we're going to do now is we're going to move that into the right position. It's not currently in the right position. And then we're going to use that entry to eliminate everything below it. So step 2 is, maybe I'll keep this here. So step 2 is we're going to swap the row of that pivot entry with the first row. Okay, so in the example, the pivot row is the row of the pivot entry. That's now the third row to start with. But we want it in the first row. So what we're going to do is we're going to interchange row 1 with row 3. We're going to make a swap. That's one of our elementary row operations. So now the pivot row is up on the top. And what used to be the first row is now in the third row position. So happily our new position of the pivot entry is at the top of this column. Now, step number 3 is we're going to add multiples of the first pivot row to the ones below it in order to eliminate, in other words, to reduce to 0, all the entries below the pivot entry. So in our example, we have our pivot entry of 3. We're going to use that 3 to eliminate or reduce to 0 all the entries below it. Well, there's 2 zeros already in place. They're happily there. We just have to get rid of this 4. So to get rid of that 4, we're going to take row 4, the old row 4, and we're going to subtract 4/3 of row 1. Okay, 4/3 of row 1 will mean that there's a 4 in that position. So when we do the subtraction, we're going to get a 0 over here. Now, also in the last column, we're also going to get a 0 over here. But this one here is a little bit more complicated because we have to take -1 and subtract 4/3 of 4, which is minus 19 over 3. And that's why there's a minus 19 over 3 in that position. Okay. Now, what we do now is that set of steps 1 to 3, we're going to repeat them in a kind of recursive fashion. So we're going to now look at the submatrix of rows and columns strictly to the right and strictly below the pivot element or entry that we already have. So that was this one here. Okay, and the submatrix formed by the rows and columns strictly to the right and strictly below the pivot element are the one that I've kind of indicated here in this little box. That's the little submatrix of the original, which is below and to the right of our pivot entry. And what we're going to do is we're going to apply the same procedures to it that we've just done. Namely, we're going to look in this smaller submatrix for a column, the first column that doesn't have anything in it. We're going to identify the top entry of that column and as a new pivot entry, and we're going to move that to the top of this small submatrix and eliminate everything below that. And then we're going to repeat if necessary. So how does it work out in this case here? Well, the new pivot entry is going to be the top of the first column in this little submatrix, which is non-zero. That's that 2. So now we're going to use that 2 to get rid of the 1 and the minus 19 over 3 below it. So we're going to make 2 row operations. We're going to say that row 3 is equal to row 3 minus 1/2 of a row 2. That will get rid of the 1 and replace it with a 0. And we're also going to take row 4 and we're going to add, okay, we have to do the right arithmetic here. We're going to add 19 over 6 times row 2. 19 over 6 times row 2 is the same as 19 over 3. So we've got minus 19 over 3 and we're going to add 19 over 3, so we're going to get 0, which is what we want. But that's also going to, those 2 steps are also going to affect this last column. So we have to also compute these values over here. Okay, so how does the half obtained? The half is obtained by taking the 3 over here and subtracting 1/2 of the 1. That's how we get the half over here. And the 19 over 6, that's obtained by taking our 4 value over here and adding 19 over 6 times the R2 value. So now we're going to repeat until the matrix is in row echelon form. So what we've just done is we've worked on this pivot entry, and now we're going to look at the submatrix, which is to the right and below that entry, strictly to the right and strictly below. So I get rid of these little things here. Whoop, not that one. If I get rid of these little red things, what we're going to be doing is looking at this submatrix, okay, this is the submatrix now, that's to the right and below this last pivot entry that we had. So we're going to apply now the same procedure, steps 1 to 3, to this thing. Okay, what does that amount to? Well, that amounts to we're looking for the first non-zero column, which is just the column that we're in. Looking for the top non-zero entry, which is the half. So that half is going to be our new pivot entry. And then we're going to use that to eliminate everything below it. In other words, to get rid of the 19/6. So how does that work? Well, we're going to take row 4 and subtract 19/3 times row 3, and that's going to give us a 0 in this place. So having done that, we have the pivot entry of 2 that we've used and the pivot entry of 1/2 that we've used. And it is in row echelon form because here is the non-leading row and it's at the bottom like it's supposed to be. And the first entries in all of the leading rows, which are these circled leading entries, they are all staggered to the right below each other as we move down the rows. So this is in row echelon form. Now at this stage already, we're usually able to say what kind of result is going to happen. So in this case, we can make a simple deduction. In this case, there will be no solution. There will be no solution to the system. How do we know that? That's because the last column, which is the column on the right side column, is a leading column. Okay, that's very important because the last right side column is a leading column. What are we talking about? We're talking about this column right here. This column here is a leading column because it has a leading entry. Right, so this is a leading column. And if that rightmost column is a leading column, then there can be no solution. Why is that? It's because the row in which that leading entry appears is representing an equation that cannot have a solution. It's representing the equation 0 equals 1/2. So if you look at this third row, the third row corresponds to the equation 0, say x1 plus 0x2 plus 0x3 plus 0x4 equals 1/2. And there's no way that has any solution. It doesn't matter what you let x1, x2, x3, or x4 be. There's no solution. There's no solution. And that's going to happen all the time when you have a situation like this, when you end up with a leading entry in that last rightmost column. So this is why it's good to pause at this point. It's a kind of a halfway point. But sometimes this is the end of the road. Sometimes you don't go beyond this. You recognize, wait a minute, there is no solution to this system. Okay, we've gotten to the row echelon form. We've recognized that that last column is a leading column. Therefore, there can be no solution. As we'll see in our next lecture, if that last column is not a leading column, in other words, if all the leading columns are on the left-hand side, then there are solutions. There's at least one solution, but there might be more. And to find out what those solutions are, Well, we have to push this row reduction algorithm further, going from the row echelon form to the fully reduced or reduced row echelon form. So we'll talk about that in our next video.